All right, thank you, Monica, for inviting me. Thank you, everyone, for coming. So, full stop. A few of you may have heard that we had announced a proof of the nonlinearity of the mapping class group. We found an error. Fortunately, we did not put it on the archive. But what I intend to do today is describe where we're at and what we can reduce the problem to, and then talk about how this criterion still holds. That's on the archive. The thing that we are now ruminating is how to apply the criterion correctly. So, as one may guess, why should one care about the linearity criterion for automorphism groups of hyperbolic groups? Well, mainly it's because you can reduce the question of the mapping class group's nonlinearity to this question here in the following way. So, first things first, we know by the Dane-Nielsen, this is all motivation right now. Motivation. Dane-Nielsen-Baer, this tells us that the fundamental group, the automorphism group of the fundamental group of the genus 2 surface. Sorry, I gotta do this. Break. This contains the mapping class group of the genus G surface with one mark point and no boundaries as an index 2 subgroup. And I guess I should say real quick what this is, just for people who may not be familiar with this. We're going to let G be, this is the oriented genus G surface with P mark points, B boundaries, and the mapping class group. Well, this would be the group of isotopies that preserve the orientation and fix the boundary pointwise. So the homeomorphism group of the isotopy. Now, it's an old question dating back at least to the 70s. 1974 is the earliest mention of it we found. Is when is this group, which I'll just denote as mod G E B, when is this group linear? So we already have some partial results. For instance, our very own Jack has shown that one. Has shown, for instance, that these groups do not emit characteristic P representations, no faithful ones. Okay, so then what we want to do is, this is button 2018. It should be BP, different P. So we'll just say Q. Okay, there we go. Sorry. Okay, so we have no characteristic P representations. So maybe the question would be, could we find a characteristic 0 representation? And what I'm going to describe is that if you could show that there are no characteristic 0 representations of this group, then there are no characteristic any representations of the mapping class group for genus 3 or above, barring a few edge cases. Okay, so we know that this contains this group as an index 2 subgroup. So really, this is linear if and only if this is linear over characteristic 0. All right? And then we also know that we have a following sequence where we go from the mapping class group with no boundaries, with one boundary and no punctures via the capping morphism, the mapping class group. Oops, sorry. Oh, where's the eraser? Oh, found it. Sorry. Okay. So we have the following short exact sequence. This goes to the mapping class group of the genus G surface, no punctures, to the genus G, a mapping class group of the genus G surface with one mark point and 0 boundaries. And this goes to identity. This morphism here is called the capping morphism. And the idea is you take your surface, which has a boundary here, and then you glue on a cap. And it turns out that this gives us, you glue on this cap and then you add a mark point to indicate that you had a boundary there. All right? And when you have this, what happens, whoops, sorry. When you have this, what happens is that if this group emits a characteristic 0 rep in an old work of Fritz from the 70s, this is actually not too bad, but implies that this is linear, or it emits a characteristic 0 representation, because the center of this group here is this group here, and this is the Dane twist along the curve. It's parallel to the boundary. So if this were linear, since this is the center, this would have to be linear. So the takeaway is that if this is nonlinear, so is this group. Okay? Let me bring this up here.
Sorry, so this perfect thing is telling you that if you have a linear group and you push in a central subgroup, you're still linear? Is that the thing?
Not necessarily any central subgroup. This is the center. Yeah, because you might do something weird where you have some sort of torsion in the center that you can't detect in linear groups. Okay, so one way to see that fact is to use like linear algebraic group technology. So you take the representation, you take the Zariski closure of the subgroup given by the center. This will be a full subgroup of the center of the Zariski closure of the mapping class group of the genus G surface with a boundary. So that's where it would come from. Yeah. Lastly, what we know is that this group here sits inside of the mapping class group of the genus G surface with P mark points and B boundaries when G is greater than or equal to 4 or G P B is not equal to 3, 0, 0. And the way to see this is you take your surface. I'm going to add a little bit more topology. Take your surface, right? Well, you push all the interesting topology into this node over here. So you have boundaries, mark points, maybe more genus. Push it all over there. And then you have the genus 3 surface with a boundary that sits inside of this as a proper subsurface. And then what you do is you like consider all the homeomorphisms that are supported on this subsurface. This promotes an inclusion of this group in here. So the idea is if the automorphisms group of this fundamental group of the surface is nonlinear, and here we're going to assume that G is always greater than or equal to 3. And I'll explain why in a little bit. If the automorphisms group of the fundamental group of the surface is nonlinear, then what will happen is that the mapping class group of the genus G surface with a mark point and 0 boundaries is nonlinear, which would then force that the mapping class group of the genus G surface with no mark points and a boundary is nonlinear, which would then force all of these to be nonlinear. So if you believe, like I do, that the mapping class group is nonlinear, you want to work with the automorphism group of the fundamental group of the surface. So that's where that's coming from. And I want to mention real quick that there is some partial results, but in genus 2. No clue. No clue, because it's like an edge case. The only way our methods cannot reach that. And not that they can reach any of them, but if our methods were to fully work, it would not reach this one because this is index 2, the outer automorphism group. So you can't do any inclusions. You cannot approach it using automorphism groups. So, and we're eventually going to relate like residual finiteness of the automorphism group to residual finiteness of the base group that you're the automorphism group of. Whereas the mapping class group of the closed genus 3 surface is the outer automorphism group. And that's not necessarily residually finite, even if the base group is conjugacy separable. Okay, so I just want to mention some quick work here, and then I'll get to the tool. Okay, below genus. In celebrated work, Bigelow and independently by Kramer, the break groups, which for us would be a mapping class group of the genus 0 surface with n mark points or p mark points, one boundary. This is linear over so this should be O2. This is O1. So it's linear over a Laurent polynomial ring. So an interesting question one could ask is like, could you find like 1 over C, not C, over, for instance, Q or some finite extension of Q? We don't know. And then later on, using this work, Bigelow-Budney and Korkmaz independently 0, 0, 0, 1. They show that the closed genus 2 mapping class group is linear. And then more examples. For the genus is equal to or less than 2. This is done by Sirocco, 2020. And then there has been a lot of work where you look at the genus being high in comparison to the dimension of the representation. I do have references for that, but I do want to talk a little bit more about what we can do. So I can tell you about those references later if you ask. But they do involve people like Favre, Lebowski, Minsky, Kaufman, Korkmaz, Koshera, all doing like various classification results of representations of the mapping class group, low dimension in comparison to genus. Okay. So for a while, it's been a question of, well, how do we even approach that the mapping class group or any group is linear or nonlinear? It's one thing to show something is linear. What do? You're like, all right, here you go. Here's a representation. But how do you show something doesn't exist? It's a lot harder. So what you do is, one approach is to go, all right, let's define variance and variance and see if that can help us.
Sorry.
Yeah.
To exhibit representation,
That's fair. That's absolutely fair. Yeah. So with that statement, characteristic P representations always exist, but faithful ones don't exist. Yeah, thank you. Okay, so I'm going to introduce some properties, some definitions. A group G is residually finite so we'll say RF if for all X in our group that are non-trivial, we have a morphism from our group G to some finite group Q such that this morphism witnesses X and Q is finite. Now, an important note here is that I'm not requiring my morphism to be surjective. All right? In some formulations, you do care whether it's surjective or not, but at least in initial applications of some of the theorems that were developed before my work with Thomas, you didn't assume that it was surjective. So what are basic properties? Well, one, linear groups are residually finite, at least assuming finitely generated. So right away, the motivating object, a hyperbolic group that we're looking at, is the fundamental group of the surface, which is linear. So those are residually finite, as we know. But if G is residually finite, so is ought G. So right away, the mapping class group of the genus 2 surface, or genus G surface with one mark point, is residually finite because residual finiteness also passes to subgroups. Okay, so the naive approach would be like, oh, well, we have a property that residual, we have some property, residual finiteness that linear groups have. Maybe that could be an abstraction, but the way it's given to us, it's not enough. We need to refine it. So what you do is this idea that was introduced by Burabi in 2010. Okay, and from now on, we're always going to assume our group is finitely generated and residually finite. Okay, the depth or residual depth of any non-trivial element in G, well, this is given by the minimum over all finite groups, Q finite, the size of Q, where there's a morphism from G to Q that witnesses X. So this is called the residual depth. And what you want to think is that having this property here, this could be used as a way to describe in the profinite topology a natural metric for which tells you how far X is away from the identity, right? So this is one point. The other point you want to take into account is that this gives you a way to complexify residual finiteness in the following way. So the RF complexity function Well, you take a generating set, which I'm going to suppress, and maximize this over elements in the envelope. Now, the exact function will depend on the generating set, but the growth rate up to pre-composition and post-composition by a constant will not. And we only care about the growth rate. And the reason why this is useful for us is the following theorem of Bourabi and McReynolds in 2018. If G is a finely generated linear group over some field, then the RF function is at most polynomial. Okay, so what this says is that if I wanted to use residual finiteness as a way to obstruct linearity, maybe what we could do is show that this function here grows faster than any polynomial. D squared. Yeah, but you can improve this. You can improve the power depending on the group you're looking at. And in fact, if G were, for instance, virtually infinite, this would actually be log of some function, log of n to some power. Okay, so the key now is like, how would we use this tool? And why hasn't anyone used this tool so far to actually get the big thing, right? And I'll explain the difficulties of actually using this theorem or computing this function. Okay, so if you want, RFG of x of n be greater than n to the d, right? You need an infinite sequence of elements, xn and g, such that the depth of xn is greater than or equal to the word length of xn to the d. All right, but to show the depth of g xn is greater than this, you need for all, that's important, all morphisms from your target, from your group, finite groups Q, such that Q is strictly less than the word length to the d power. When we evaluate phi on x, this is trivial. So you need, in some sense, an almost a complete understanding of the finite index normals, finite quotients of your group to really compute this. And this property doesn't even characterize linearity. You have examples of meta-abelian groups. That are not linear, meaning no faithful representations over any field, but are faithful over a product of fields. So we run into some problems here, right? The first problem is you need to know a rather complete understanding of the finite index normal subgroups of your group, which for the mapping class group is very hard. We have lots of conjectures about the finite index structure, finite index subgroup structure of the mapping class group. And this doesn't even characterize it. So we got to refine our question even further. Okay, using the proof that if you're faithful over a field, you have polynomial residual finiteness, you can use that same proof to show that this has polynomial residual finiteness. I don't know, but what I'm going to do is I'm going to give a characterization for hyperbolic groups in terms of a restricted family of finite quotients. Yeah. Yeah, it's the bound you think it is. If you know the bound for RF of G gives a bound for RF of H.
No, not the H. From G to R.
Oh, no. You get like a super exponential bound. Yeah. So like just knowing it's the automorphism group without any further properties, you can't get a good bound at all. Yeah, thanks for the question. It's just not a good one. As I write up this next definition, the way you do it is you go, oh, I know the quotient, and I pass to the characteristic core of the finite index normal subgroup. That can be very big. The only balance you can get without actually knowing what the group is like factorial. Okay, so we're going to let F be the family of finite simple groups. Okay, and then G is residually F if we can detect every element of our group G, it's non-trivial, with a morphism to a finite simple group. So Q here, and phi of x is non-trivial. Okay, so you can then define the residual depth, the depth function relative to F, right? So this would be the same thing, but we only look at groups that are inside of. And then I'm not going to formally define this because it's clear what it should be. Okay. All right. So let me get my references here. You can actually characterize linearity of hyperbolic groups using this function here. So we have the following theorem, 2008, through Robbie and McReynolds. Let's say that G is non-elementary hyperbolic group. Then G is linear if and only if RF, G, fancy F is a most polynomial. So this rectifies this issue that we have up here, and that if you have a hyperbolic group, you know precisely when it's linear in terms of this growth function. And if you're wondering about what happens if your group is not residually finite, well, then it's not linear. And then this function would have to be infinite. Yeah. Mm-hmm. See, that's a good question, because I didn't assume that this was a surjection. All right. This concern will come up later. So what about this group? Well, the issue is, while we know, if we just choose not every morphism of a group G to some finite group Q will induce a morphism of the automorphism group of G to the automorphism group of Q. You have to have a structure, some properties of the finite index normal subgroup. So let, as before, let F, and I'm going to restrict my family a little bit now. So instead of all finite simple groups, we're going to throw out the alternating groups, the sporadic groups, and any mystery groups that may be hiding that, assuming you don't know the classification of finite simple groups. I believe it, but let's not worry about it. Let F be the family of finite products of finite simple groups of Lie type. It's still, yeah, it's no longer just simple groups. The reason being is that your group may not emit any characteristic quotients that are finite simple groups, but you will, if you have a quotient that's a finite simple group, you will emit one that is a finite product of finite simple groups that are characteristic. Okay, and we're also going to let, so we say G is so it'll be a family, not necessarily all of them. Okay. You say G is residually right if, as one would expect for all X and G, there's a morphism, and now we are going to assume it is surjective. This will be a key point later, and it will actually justify why we'll have to pass a finite index subgroups eventually. Where Q is an F, and Q is an F, phi of X is non-trivial, and the kernel of phi is characteristic. So, well, we can define the depth in a similar way, where we maximize over all morphisms of this kind, two groups in F. And then we can also define the residual finiteness function okay. So there is one last invariant I need to add before I can actually form and state the theorem. So any finite symbol group of Lie type, well, this will be sitting inside of some, well, let's just say it's defining characteristic P, right? The defining characteristic. This will sit inside of some linear algebraic group defined over the closure of the finite field of P elements. Well, there will be an E such that G is contained in the FPE points. Right? So it'll be the minimal degree of an extension of the finite field F for which it is defined. So the reason why I define that is you can add a letter here, E, meaning that all the terms in the finite products of finite simple groups are defined in a field whose extension is at most field of the defining field has extension of most E over the base field. All right, so here's the theorem. Okay, 2025.
What's allowed in finite product?
Finite products of finite simple groups of Lie type over finite field, and they can be any product. So if you have a finite product of finite simple groups, let's just say all the finite factors have the same defining field, they will be a quotient of a subgroup of this. So instead of doing that, what I'm going to do is I'm just going to give an informal definition. So when I say E, I mean if you have a group of the form PSLN at P to the K, right? So this is a classic finite simple group of Lie type. I want K to be at most E. And then like if you have groups of the form PSL3 PK cross PSL5 PL, I want K and L to be at most E. So part of the data of a finite simple group of Lie type is the linear algebraic group. So here it would be like PSLN, and the field is defined over. So here this would be at P to the K. So I don't care what the what linear algebraic group is defined over. I do care what the degree of the defining field is over the base field.
All the factors would be
Bounded above by E. Yeah.
the same.
No, not necessarily. So yeah, you could do this. Yeah. Okay, so we have two parts. Suppose there is a E, we'll say ED greater than 1, and a finite index subgroup in the automorphism group of G. Here G is a non-elementary hyperbolic group, a non-elementary hyperbolic group, okay? Such that RF, and then we'll say G intersect with B, and then we're going to look at the amorphous quotients. And let me explain what this says. I have a G here, hyperbolic group G. I have a finite index subgroup B, which will intersect the group G. This will be a finite index subgroup of G, which will be invariant under the group B. So you can look at morphisms from G intersect B to finite simple groups of Lie type or finite products thereof, whose kernel is invariant under the group B. So that's what this function here is saying. So if this function is bounded above by some polynomial, then ought G is linear. Ought G, because when you apply this, it'll tell you that B is linear. B is a finite index subgroup. Yeah, finite index subgroup of ought G. Finite index subgroups representations promote to the ambient group.
That would be when B is equal to.
Yeah, that's right. In fact, what you can do is you can replace this entire story with some automorphism group of automorphisms of your hyperbolic group G that contain G. Yeah.
So this theory is under the hypothesis that G is residually.
If G is not residually finite, then ought G. Yeah. Oh, if it's not residually F car, then this doesn't hold. Yeah. But yeah, I guess like you wouldn't want to consider it otherwise. Yeah. But the thing is that if, and in fact, what you could do is you could just say all finite simple groups of Lie type and finite products thereof. And then if you have a finite index subgroup that satisfies this property, then your automorphism group is always linear. The only reason why you would want to restrict to a specified family of finite simple groups is if you want to construct the representation. Because what will happen is, excuse me, what will happen is that if the family of finite simple groups are finite products of like PSLDP, where P varies over the primes, you actually get a representation into PSLD ultra product of the defining fields. Okay. So the other way, the reason why I had to put this E in here is that other way doesn't hold, right? So if ought G is a subgroup of GLDC, then there exists an E and some D big D and a finite index normal subgroup such that RF B intersect G F, and then we'll say B E like so. Okay, so this is saying, and like the reason why we have to passive finite index subgroups is because you may not have any morphisms from your group, even given a representation. You may not have necessarily morphisms from your group to a finite product of finite simple groups. The reason being is that, let's just say you want to use strong approximation, right? Strong approximation only works when you have a connected, simply connected linear algebraic group. But given a representation, so you throw your group into GLDC, the Zariski closure may not be connected. It may not be simply connected. But if you pass to a finite index subgroup, the finite index subgroup will be Zariski dense in some connected, simply connected linear algebraic, semi-simple linear algebraic group. Right? So that's why you have to pass to a finite index subgroup here. And if this were to be over FP bar or some transcendental extension of FP, then you would have to drop the E, because there the defining degrees can be as big as you want. Okay.
See why this is not a
If I put yeah, it's because it's C. If I put FP bar here, so if aught G sits inside of GLD FP bar right, then same picture, but R F G intersect B F E N. So that you can't control the extension degree.
Very basic question. So being for a finite geometric group, being linear over characteristic 0 is the same as being linear over C.
Yeah. So the way to view it is this: if you're linear over characteristic 0, right? Then you're linear over some transcendental extension of a finite extension of Q. Then you pass to some bigger representation, and then your transcendental extension of Q. Each one of those a finite degree. Then each one of those indeterminates, you just plug in algebraically independent transcendental numbers. This will embed your group into C. Any questions before I continue?
That B is the finite index of it?
Yeah, that's right. Okay, so I want to make some comments here. Okay. So one of the reasons why we have to choose a invariant or like epimorphism whose kernel is invariant under the automorphism group is that, so thing one, if we have a morphism from G to Q, any finite group, not just necessarily ones coming from a family F, such that kernel Phi is characteristic, then there's an induced morphism so if I have a surjective epimorphism to some group where the kernel is characteristic, then I get a morphism of this way, right? 2, we want to note the following. We know what this is when S is a finite simple group of Lie type. We can write that down. Yeah. Yeah, absolutely. Well, see, the thing is, Bun's theorem, for us, we wouldn't even have to worry about this, right? Yeah, G is the surface group. Yeah, so if the generality here is like kind of obfuscating the picture, yeah. Yeah, just assume it's a surface group. Then like, yeah, if you assume it's a surface group, then you don't have to worry about this. And then it becomes an if and only if. Yeah. Yeah. So Bun's result allows us to not worry about the scary characteristic P things. So if one were to want to investigate this question.
Is there a version of part of the theorem in for what characteristic P representations?
I-
What different class have?
I don't know.
I'd imagine you could trade in the E for fixed characteristics.
Probably. Yeah,
It's not that.
it's not a part of the result. Yeah.
Here again, F is the family of all finite simple groups.
Yeah. Mhm,
And all
mhm. Yeah, but if you were to fix your family, right? Like I was saying, like PSLND, as you vary over prime powers or something like that. More questions? Okay. So the first note is we have this. Second note is we have this. We know what these are. We first know what all the finite simple groups of Lie type are. And through the work of many, many people, we know what the finite simple groups of Lie type and what their automorphism groups are. So this here, because it's a finite simple group, the automorphism group of this group, this is given by automorphism group of S to the L power semi-direct symmetric group on L letters, where this acts by coordinate permutation, right? And then the other thing we want to know is that we have the following lemma. Okay, so suppose G the finite simple group of Lie type. Right? Okay, one, and then where G has a projective representation of degree D.
Maybe Q or F are method of this.
What's that? Yep, sorry. Okay, suppose SL is a finite simple product of finite simple groups of Lie type, or yeah. Okay, where we have this. So it has some projective representation of degree D, and the defining field is FPE. Okay? Then there is a constant C such that SL emits a faithful representation over C times L factorial L D squared of what's that? Yeah. So if you have the following conditions here, right, then we can actually, there we go. Yeah. Otherwise it wasn't anything. Okay. If we have these conditions on S, then we get a faithful representation over FP of the automorphism group of SL. So what does this say? This says that, yeah, GLC of L factorial times L times D squared. So it's some function, right? Some alpha function in the number of factors of S, right? And the projective dimension of the original group S and the defining field of the group S. So if you know, yeah, it should. It was a function, but I'm just going to say there's a function in C. And
could be like a factor.
It is a factorial in general. Yeah, so if we know that, and I got 3 minutes. All right, if we know that every element can be detected with a morphism from G to Q, where Q equals S to the L, where we bound the extension degree, we bound L, and we bound the projective rank, then we actually get then aught G is residually GL C of L B squared FP. Okay, that's the meat of the theorem is actually just showing once we know the theorem, once we have the conditions, we want to show that this first part. The second part is just an application of this lemma. The last thing I want to say is kind of like the state of affairs. I got like 1 minute. Okay. Only thing I want to say is the following. We know aught FG is nonlinear when G is greater than or equal to 3 by Harmonic and processive. So when we apply our theorem, okay, we apply our theorem to F aught of F3, we know that for all finite index subgroups, R, F, B intersect F3, F, E, okay. So the last statement I'll make is that what we did is that we were able to reduce the consideration of all finite index subgroups of finite index normal subgroups of the mapping class group to only finite index normal subgroup, finite index characteristic subgroups of the fundamental group of the surface, so that the induced map is null homologous, right? And what this says is that if you can reduce all the way to just maps that factor through the free group, then you actually got it. The issue is that there exist null homologous maps from the fundamental group of the surface group to finite simple groups of Lie type that are characteristic, that are also null homologous, that do not factor through a free group. So that is the current state of the art. Okay, thank you. Yeah.
Can you repeat the last thing you said about null homologous?
Okay. So there are two homological variants associated with the surface. There's first homology and second homology. When you go to a finite product of finite simple groups, right? The induced map on homology was trivial in first homology. So then the only homological variant you have is second homology, where we send the fundamental class. And null homologous means that we kill off the fundamental class. So there exists infinitely many epimorphisms to finite simple groups of Lie type whose kills off the fundamental class in second homology, but does not factor through the free group.
The thing that you said that reduces the automorphism?
Yeah.
I mean, this is just, am I supposed to deduce this from something you said before, or are you just saying that?
I was just, we know how to do it. Yeah, yeah. It involves strong approximation, as one would guess. Yeah, but like, we can reduce it down to null homologous maps, ones that induce trivial map on second homology. And what we want to do is we want to reduce all the way down to only looking at the elements coming from here. If you can do that, then like the whole program would be done. But since we haven't done it, right, it's not easy. At least it's not easy to us. Yeah.
So in this theorem, the if and only if statement between the polynomial growth and the linearity, I mean, can you say a word how hyperbolicity helps to
Yes.
fit the representation?
Yeah. Yeah. The reason why hyperbolicity helps is because it allows you to control the order of elements when you look at their image in the following way. Hyperbolic groups have non-trivial common multiples. So if I have a subset of G, where G is hyperbolic, non-elementary, a common multiple is just an element of this group here. And when you have a non-elementary hyperbolic group, this group's always non-trivial, right?
The bar for what's T?
T is in big T, which is a finite set, in G minus 1. This here is a normal closure. So not only do you always have a non-trivial elements in here, you have that there exists an element x not equal to 1 in this group here, so that length of x is the most some constant times the order of the set T, the size of set T, times the max of sizes of elements in T. Okay? And then what this does is that if I take an element, and here I didn't assume these elements in our set here, T, are distinct, right? So what you can do is you can actually say, if I take x1 or x squared, x cubed, all out to xk, and I let such an element here would be called a least common multiple. X equals least common multiple of this, not x, we'll say y. If y does not vanish, then the image of x has to have order at least k. And you use this to start doing estimates when you apply the residual finiteness growth thing. For instance, one way to see that is if I have a morphism that goes from my group G to some group HX, LX, right? So that this is non-trivial, okay? Then you have that the size of this can be chosen to be at most the word length of X, or yeah, the word length of X to some power at, and we'll say this is YK. So, okay, you have this. What this says is what this property here gives us is that the order of H Lx is at least K, right? So not only do you get an upper bound, but you can control the lower bound of it. And we have that this here is bounded above by X, K to the D. Then what you do is you're taking the natural log of this whole thing. This comes from right here. Because since yk is non-trivial, yeah, my fault. Since y is kind of non-trivial, all these independent elements here have to not vanish. So k has to be at least, this has to be at least the size of k. You take the log, and then you have that lk is bounded above by a function in d and k, and you just drop everything out. And what this allows you to do is it allows you to bound the multiplicity, or the number of factors that shows up. So this is one of the ways that you actually use hyperbolicity. The other way you use hyperbolicity is you bound the projective dimension of your groups H.
Your function is defining for, we want groups that are reasonably finite using characteristic quotients that surject products.
Yeah, that's why you have to pass the finite index.
I mean, I guess it seems pretty non-obvious to me that any groups have that property.
Well, any hyperbolic group that's linear has that property, up to finite index. Because it was like the thing I was saying earlier. The way you would produce these finite quotients would be to reduce mod p. Yeah, but like strong approximations makes it so you have to have it connected. Yeah, it's a strong approximation thing. That's right. Yeah. There are some modern treatments of strong approximation that actually don't even use the classification of finite simple groups. Specifically, if you were to do one over global fields, so like Q or a number field or something like that.